Okay, this is the overview. It actually doesn't match up with my slides very well. So a little bit of background on GSM so you guys are kind of up to speed on what's happening. Then I'm going to talk about base station and then baseband stuff and then a conclusion. Actually, yeah, ignore that slide. It's wrong. Okay. So the GSM protocol is absolutely fucking huge. It's made up in dozens and dozens of documentation. Like there are these 1,000-page PDFs that you have to read. So, for example, to understand the L1 layer, which is the radio encoding layer, you have to read a 500-page document called GSM 0508. If you want to understand how the L3, the actual application layer, works, you have to read GSM 0408, which describes the application layer. You have to read a separate GSM document which describes how the structure formats are defined, and then another one that describes how the definition of the structure formats are encoded. Right? So you need to read 3 documents just to understand it. Or you could do what I did and cheat and just read the source code to GSM implementations, as well as 0408. So basically, if you're getting into GSM, you can skip most of it and just do 0408. It's the simplest one. It helps if you have an understanding of telephony to begin with, how it's set up with basically signaling and data layers. But anyway, so at the lowest level of GSM, the actual RF part, I stole all of these pictures from Wikipedia, by the way. So like my art isn't anywhere near this good. Basically, the important thing to take away from this is that GSM is based on TDMA, which is time division multiple access. So it's all based on clock timings. The stream of bits in the air is actually decoded based on time. So you have to sync the clock in your phone to the clock in the base station correctly in order for you to be able to interpret the bits back and forth. The important thing here is that there's actually only a very, very small amount of data per time slice, per time slot. So each of these things is called TS for time slot. There's TS0 through TS7, so there's 8 of them. You pack them together and you have a frame. So 8 time slots is 1 frame. You pack those together, you can either have 26 or 50. So basically you have 27 or 51 of them in total, and those are called multi-frames. You add multi-frames together, you get super frames, which take 6 seconds to transmit. And then you add super frames together and you get hyperframes, which take 3 hours, like 3.5 hours to transmit. So the hyperframe is important for A5, which I'm not going to talk about because I don't care about it. But basically, the frame position within the hyperframe is used as part of the encryption input. So that's important for A5 stuff, but not for us. Essentially, each of these time slots has 23 bytes of information. So when we do our fuzzing attacks, when we're trying to fuzz the phone, we only have 23 bytes to play with. So we could actually do a complete exhaustion of all of the possible combinations in a very, very short space of time. It takes us, I think, 3 days to run through a complete exhaustion of just one channel. Right? Okay, so we have these 3 layers that go into GSM. Everything in GSM is it's compacted into just sets of initials. So the layers are called very creatively L1, L2, and L3. Sometimes you'll see the abbreviation L123, meaning all of them together, or L23, meaning just layer 2 and 3. Important one over here, L1, that's the lowest level, as I said before. That's slightly above the radio level. That's literally just how things are encoded in the air at the radio level. It's kind of boring. There's not a lot you can do with it security-wise. If you get it wrong, then the phone just is unable to decode the bits, or the network equipment is unable to decode the bits. Like, there's not a lot you can do there. L2 is actually quite thin. It basically determines which of the L3 state machines should receive input from the L1. So L1 decodes or encodes the data, passes it to L2, and L2 looks at it and figures out which part of L3 should handle it. Then L3 contains the application layer stuff, and that includes things like CC, MM, and RR. Right? So CC is call control. Call control is used very obviously for setting up and tearing down telephone calls, and MM is mobility management. It's basically used for authentication, and for moving from one cell to the next cell. So it deals with basically the auth part of the GSM stack. And then RR is radio resource, and it's used for dealing with opening channels and closing channels and so on. So those three things, CC, MM, RR, L123, like we've got tons of these, so everyone should keep up, right? Then we need to look at the sorts of channels that you have. So as I said, like you've got these time slices. Each time slice will be assigned to a channel, typically. So for instance, C0 TS0 is channel 0, time slot 0. That's the BCCH, it's the broadcast. So if we go through these quickly, you'll see that we've got BCCH, which is the broadcast control channel, FCCH, which is the frequency correction channel, SCH, which is the synchronization channel, and the CBCH, which is cell broadcast channel. Basically, BCCH pours out all the information about a cell. So if you're using if you have a BlackBerry and you have it set up for the engineering screen, like everyone's done that, right? You can hack your BlackBerries and like get engineering tools. If you do that, it will have a screen which lists things like all of the available ARFCNs, the available cells, and several of the timers and so on. All of that information is sent over the BCCH and sent as system information messages. So there's SI1, SI2, SI3, SI4, 5, 6, 7, 8, up through 16, but only 1 through 4 are important. And once again, we're not going to deal with those specifically. So all of these are basically broadcast channels. They're unidirectional. They only go down from the network side to the phone. Okay, so there's the downlink from the network to the phone and the uplink from the phone to the network. Most of the attacks we're going to be looking at today are uplink, so they're from the phone to the network. They're much more interesting. All right, then we have control channels. Okay, these are actually useful for us. So there's the paging channel, the PCH. The paging channel is used to announce to a phone that there's an incoming SMS or an incoming phone call that it needs to respond to. There's the RACH, the random access channel. RACH is used by the phone to request a channel. So it sends a request up. I'll go into this in a bit more detail. So it sends a request to the network, and the network allocates a channel and sends it back down. It sends it back down on the ACGH, the access grant channel. Right? So these three are actually kind of critical for us to understand GSM. Then once you've opened a channel, you're going to get a SDCCH. It's a standalone dedicated control channel. The particular one that you have isn't really important. What's usually critical is how it gets used on the application side at the back end. So there's fast association and slow association, which are based on authentication levels, as I recall. And then this ACCH, I'm not sure what that is. Right. Now, the important thing to remember about a GSM channel is that they are fucking slow. It can take 2 to 3 seconds to open a channel. Right? They're not instantaneous because it's all based on time slots. So once you make your request, it can take a while for the backend to have a slot available where it can respond to you again. Right? There can be really, really like huge amounts of time that get wasted in there. That hurts us mostly on the fuzzing side when we're using our our base station to fuzz phones, because opening a channel can take a long time. It so far hasn't been a huge issue, but it's something to be aware of. And also there's a lot of channels, right? So everyone's comfortable with that, right? Like the SDCCH, PCH, AGCH, RACH, right? L123. Yeah, we're good to go? Any questions? No? Awesome. Okay, so now we're going to look at how a channel is opened. Opening a channel is actually fairly straightforward. Okay, so the phone makes a request on the RACH, and this request is basically made up of a random 25-bit value. All right, so you can see like this is strong security at work so far. So the random 25-bit value is chosen by the phone. It sends a request to the tower. The tower will find an open channel and put that information in the access grant channel response, and it will send back a response saying the person who made request 01 now has channel, this time slice, this channel, this frequency, blah, 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 right? So that information comes back, and at that point the phone can then attempt to make the connection by using that information to transmit, right? So it's pretty much asynchronous. The phone makes a request. If it gets a response, then it can then associate on that channel. Right? All good. Okay. The other setup is, so that would be if the phone initially wants to make a call itself, if it's trying to contact the network out of nothing. If, on the other hand, there's an incoming message or incoming SMS or an incoming phone call, the tower will broadcast over the PCH. It will broadcast. The person with this ID number has to, basically should talk to me and get a channel. So it'll send a broadcast out on the PCH, and these are very, very simple. It's a 32-bit value, which is called the TMSI. It's the Temporary Mobile Subscriber Identifier. And it sends that out, and then the phone that has that TMSI will respond. And it will respond by sending an RACH, right? Gets back on the ACGH, and then you've got an LCH. Yeah? No questions? Awesome. Okay. Part of the funny stuff that happens with this is, for example, the way that older phones that didn't have a lot of memory and didn't want to generate random values or use a tick counter, they would pre-select 32 random values and burn those into the firmware. And then they would just use a pointer to iterate through those 32 values. So that's how they would get the random values for this stuff. So you do get collisions fairly frequently. Right? I mean, 255 bits is not a lot of space. Right? This is sort of what a typical cell station will look like. So the BTS is the base station system, the BSC is the base station controller, and the MSC is the mobile switching center. Right? Everyone's got that? No problems. So the MS, or the mobile station, will connect to one of the ARFCNs, which is the absolute radio frequency control number, or code number. All right? This isn't too much for anyone, is it? Okay, so ARFCN is basically a specific subset of the GSM band that you're using for your communications. So of the GSM bands, which is like 850, 900, 1800, and 1900, there's actually subsets within that of 200 kilohertz, megahertz, some value that's fairly small, and those get paired together. So there's an uplink and a downlink. And then those get divided. So there's 1024 of them in total, going from 0 to 123. And there's a simple algorithm to convert from a ARFCN number to the specific frequency that you're using. And it's basically like you add 20 and multiply by, or you multiply by 20 and you add the base value or something like that. It's very, very simple. Pretty much the important takeaway from that is the low values from like 0 through, I think, 256 are GSM 850, 256 to 512 are 900, 512 up into the low 800s or so is for 1800, and then there's a crossover from 1800 to 900 where 623, which is, for example, the ARFCN my BlackBerry is on right now, 623 is either 1900 or 1800. And unfortunately for the demos over here, it's 1900. So as I mentioned, the demos don't work on 1900 band. All right, so that's at the actual tower end. So usually they'll have several ARFCNs per BSC, and those ARFCNs have very, very low levels of logic. They're not very sophisticated. All they do is the actual radio encoding and decoding, and they pass all the information back up. Then the BSC will monitor several of these and use that to send information back up to the MSC, and the MSC will basically keep track of the regional information and then push it back even higher. So the base transceiver station here will talk to the phone. It'll basically have an Ethernet connection or sometimes a direct radio link back up to the BSC, or it'll be on-site. BSC will go back to the MSC, and so on. It's pretty straightforward stuff, right? More interestingly over here is the MS, which talks to the BSS. Sorry, so all of this together is called the base station subsystem, and the base station subsystem is what we're going to be attacking in the demos that do not work. Okay? So the base station subsystem talks to the phone. It's in communication with the MSC. The MSC is in communication with the back-end stuff, which is the HLR, which is the home location register, and the VLR, which is the something else location register. Basically, the HLR is used for people who are on the same network. So if you have an AT&T phone and you connect to the AT&T network, you'll use AT&T's HLR, right? And that'll be a huge database that lists where you are, your phone is turned on, last time you updated it, a bunch of information like that they will use to be able to contact you. So when a phone call comes in, it will go to the HLR. The HLR will say, yeah, that particular phone is located at this BSS, route the data to there, right? And it will get routed to that BSS, which will then send out a paging request, and the phone will, like RICH, AGCH, LCH, and so on. The VLR is used for when you're roaming. So if you're on someone else's network, they will use the VLR to contact basically internationally or to contact the other networks to get information about you. So it's going to be used for authentication. And in order to do that, they have to have a lot of information from the SIM card. Most of the time, that involves going out and contacting your home carrier. All right? So the HLR and the VLR are very, very important in terms of the way that a GSM network is set up, in that they are used for authentication and keeping track of all of the users. When we were doing a pen test like a year ago in Indonesia, they had used their HLR to run their web server as well. And we accidentally DOSed their web server, which we found out about when their whole network went down. So they were very, very upset about that. But yeah, it's their fault. They shouldn't have done it. But basically, HLR is pretty critical stuff, okay? Within the mobile GSM environment, there's a few key identifiers that are useful to know: MCC, MNC, IMSI, and the IMEI, right? So the MCC is the mobile country code, and with the MCC, you can tell which country, basically, a specific phone number is from, or a specific IMSI is from. The MMC is the network code. So, for example, in the US, I think the mobile country code is 360, and the mobile network code for T-Mobile is 26, right? So, by having those values, I can know that a particular IMSI is from the T-Mobile in America network, or if I'm setting up a spoofing base station. So the base station, when it's part of the stuff that goes out on the BCCH, on the broadcast, is the MCC and the MMC. So mobile phones can figure out whether they're supposed to associate with that particular tower or not. So the MCC and the MCC are very important. They're the key identifiers that are used for networks within the GSM environment. The IMEI is a serial number that's burned into your phone. It's supposedly unique per device, but there are issues with that. So if you have very, very cheap, like in Thailand, what we would call China Mobile, which are MTK-based chipset phones, they're very, very cheap. They cost about $20. They usually last about a week, and then they fall apart. But it's very, very popular everywhere in the developing world. There's a lot of MTK phones. What happens is the MTK phone, when you're putting together a copied Nokia or a copied BlackBerry or something like that, you basically buy an MTK board and then you just slap on whatever case you want. So the MTK board will come with an SDK, and it has things like how to get an IMEI, or here's an example IMEI. And one of the things that happened was in India, they found that there were 20 million phones that had the same IMEI, right? So they were all using these MTK chipsets that had been pre-burned with like an example IMEI, like here's how you would set one up. And the guys that were making the phones were like, well, it would cost us 15 cents to figure out how to change it, but our profit is so slim anyway, like we'd rather keep the 15 cents, ship them. And the Indians then, recently they've had a thing where if you do not have a unique IMEI, they will bar you from the network. So they kick 20 million people off their networks, right? So apparently those IMEIs were very popular for terrorists because obviously you're one of 20 million people all with the same phone ID number, and you could buy a pay-as-you-go SIM card. So anyway, IMEIs are fairly cool. IMSIs are much better. The International Mobile Subscriber Identifier number, right? So here's the first time you'll see this awesome graphic. I use it very heavily. Right, basically your IMSI is on the SIM card, your IMEI is on the mobile device. Okay? The way that this information gets into the GSM network, which over here is shown by basically the MSC, the HLR, and the VLR, is by something called a location update request. So the first thing that happens after a phone has opened a channel is it sends a location update request. Right? Phones are also on a timer, which is called, I think it's the 32212 timer, which every time that times out, it triggers a timeout, and they do a new location update request to keep the network informed. And if it's turning on for the first time, it'll do what's called an IMSI attach, which is where it notifies the GSM network that the phone has now been switched on, and that particular IMSI is located at this particular BTS. So basically, this data gets sent up to the BTS. Part of the information that's included in that is called the LAI, which is the location area information. The LAI is from the BTS. It's part of the BCCH. Everyone remembers BCCH already, right? It's the broadcast information that gets sent out by the BTS, obviously. So the BCCH includes the LAI. The LAI gets included with the IMSI, which goes up through the MSC. Yeah? I'm seeing a lot of nodding heads. So anyway, the IMSI and the IMEI will be sent in a location update request. The location update request is also used for authentication. So the only way that a GSM network knows a particular user is who they say they are is based on the location update request handshake. So location update request goes through. If it gets all the way back to, say, the VLR or the HLR, and that particular user hasn't been authenticated for the action that they're performing, it will do a enciphering request. So the ciphering request says, let's turn on A5. And when that happens, you have to have KI, which is the secret key stored in your SIM card, in order to turn on ciphering. If you can turn on ciphering, then you're authenticated to the network. If you cannot turn on ciphering, you are not authenticated to the network. The way that an IMSI catcher works, so IMSI catchers are very popular with police. They take them to parades and riots and things like that, and they try and capture the IMSIs of all of the mobile phones of all of the people that are there. The way that that works is it impersonates the network, so it sets up a fake BTS. It broadcasts the spoofed information just using the MCC and the MMC of your target network. When the phones associate with it, one of the drawbacks with GSM is that the network doesn't authenticate to the phone authenticates to the network. Right? So there's no way for the phone to know that it's not talking to the correct network. So when the IMSI catcher rolls out there and it gets a phone to associate with it, what happens is the phone sends the location updating request, which includes the IMSI information, and then the BTS says, I'm sorry, you're rejected, try a different frequency. And then the phone will reconnect to a different BTS, a real one. And in the meantime, the police have now captured the information of that particular subscriber, and they can then go to the network and they can get their information. So that's one of the ways that they use for tracking people at marches or at like the G20 stuff that happened recently in Canada, wherever it was. But yeah, it's very, very basic stuff. IMSI catching is like trivial. And I say that only because someone's doing an entire 1-hour talk on IMSI catching. Okay, so everyone is completely up to speed on GSM stuff, right? PCH, AGCH, RACH, IMSI, IMEI, no questions, right? Okay, so what, like, I was basically tasked with by my boss is to work on GSM attacks, and fortuitously enough, it coincided with these German guys developing an open source baseband for this type of phone, right? These phones cost about €5 on eBay. They have really good battery life. The design spec for the board was leaked several years ago, and there was example source code leaked as well from Telefonica in Spain. And so the German guys were able to build a functioning baseband on the phone fairly rapidly, and I've been working with that project to develop client-based attacks against the networks. My first get-up was a little bit ghetto. I couldn't find the right cord, so I had to get someone to make it for me, And then the pinout that we had was for a DB9, and we couldn't find a DB9, so we bought an old modem and we hacked that up. And then we had to get a DB9 to USB, and then from the USB I was able to get that into the laptop. So it was very, very ghetto, but it did work. So using that setup, which now is done with basically a cable and one of these phones, I'm going to talk about 3 attacks now. The first attack that I put together is a very, very simple one. It's called Rachel. Unfortunately, I didn't discover it first. I'm very disappointed in this. There's a guy called Dieter Spar who talked about it last year at DeepSec. But his graphics aren't anywhere near as cool as mine. So that's cool. Basically, the way that this works is, as I mentioned, so we have the RACH request that goes out. Then you get an access grant response. Then you open a channel and you do a location updating request. And it's only at the location updating request that there's any authentication, right? So anyone can send an RACH, just like that's the way it works. So the technique with this attack is to use the phone to send out RACH, like basically RACH attacks, RACH requests in excess of the number of channels that can be allocated by the BSS. So there's actually a strict limit on the number of channels that are available. As I mentioned, it's all timing based, so they can't just add new ones. And the number is fairly small. You can basically get about 1,000 users on a cell, right? So if you can send more than 1,000 requests, you can take down that particular cell. So we just flood requests, right? Very simple stuff. And what happens is no one else is able to use that particular cell to allocate a channel and make a phone call, right? So it takes down even emergency services, right? It's fairly cool. Unfortunately, as I said, the phone I have here doesn't support the band that we have available. And the video I wanted to make, I didn't get around to making. So if you can all just imagine I'm trying to make a phone call now and it doesn't work, I must be on AT&T. No. Right. Like I can show you the demo running and not doing anything if anyone wants to see that. But here's the graphic of the basic idea that goes on. So we take our evil attack phone and it starts sending RACH requests to the BTS. When we tested this, we thought that we were only going to be able to take out one BTS, and we thought that that would be like okay. But what we found out was we actually took out the entire area, because the way that it worked was that BTS was backed up to a base station controller that was very, very weak. And when it had all the requests coming in, we accidentally knocked over the base station controller, and like the whole tower went down. So my office was without any coverage for like half a day. It's a little bit embarrassing. So if we take out the BSC, then we end up taking out both the BTS and the mobile phones. So no mobile phones can use that network. However, all of the back-end systems, they typically don't have monitoring for this sort of situation, right? This is basically very, very peak usage. They don't test for this all the time in all the places. So this goes without being detected, right? No questions. Yes. I have absolutely no idea. Our belief is that the BSC allocates channels, so it allocates the channel information, and it has to keep those open for a certain period of time before closing them, right? So after it makes an assignment, it will have a timer for, say, 5 minutes, and if there's no, if that channel is not opened within 5 minutes, it will close that out and then put it back on the queue to be used again. So what happened was we allocated so many channels that the timers never timed out before there were new ones, like new requests coming in, and as a result, either it took down, like it might have been like a small 100 megahertz PC that couldn't handle like more than 8 megabytes worth of requests, or something like that. Basically, like the belief is that there were so many requests coming in over the channels that the computer allocating channels ceased to function. No, typically the BTS isn't that intelligent. Typically the BTS only does radio conversion. It only does the layer 1 stuff. And then the layer 2 and layer 3 is implemented further back. That's the usual setup. It allows the cost of the BTS to be kept low, and then you can deploy multiple BTS systems and have only one BSC, which is much cheaper for a telco. They can spend $50,000 or $60,000 on antennas rather than $150,000 at a go. So usually the BTS doesn't have a lot of information on it. So yeah. I'm sorry, I didn't hear the question. Yes, people who are, the question was, are people who are still on call, do they stay up? Yes, the calls that exist, they're existing channels, those don't get taken down, but people who try to make new calls, who have incoming SMS or incoming calls, that ceases to work. Right, this would be information on the cell that we have over here. It's actually, this is in Hangzhou in China. It's not the correct information. If it was ARFCN 96, I could do this. Instead, it's 623, which is too high. So that's what we would be going after, but we're not. Does anyone want to see the software just kind of running and like dumping out output? It looks pretty awesome. Fuck yeah, let's do that. Right. I'm not very good with computers, so bear with me. I need to... for the attacks or for my personal use? For the... Okay, you can all see that. For the attacks, it's a Motorola C123. You can also use the Motorola C118. They're actually identical boards inside. If you go on eBay now, they're probably going up in price like crazy. But yeah, grab these things. Then you get another €5 cable. You should get the good ones that are USB, like this. And then it's this tiny little headphone jack, actually, that works. Right, so... okay. Oh, that looks kind of horrible. Okay, so we start up Osmocom. Oops. All right. Bear with me 1 second. I have to get my demo set up better. Rachel minus A. Okay, so we're running Rachel, we're running our loader, and now the battery is dead, I bet you. All right. There we go. Okay. Okay, so that's loading the firmware, and now it's trying to sync to the right ARFCN, and it's failing miserably. And here you can see it's not working at all when you get that error response 255. But if it was working, what you would see is loads of purple RACH request messages showing up. What's failing right here is the sync request. It's trying to synchronize to the BTS, right? So unfortunately, I need to have at least 60 dBm on power for it to work, and I bet you it's running at like 90. Yeah, 92. So if we all go outside and find where the tower is, and I can get close enough, then I can probably show you this attack.
Are you attacking T-Mobile or AT&T?
I'm actually attacking T-Mobile. AT&T doesn't have a GSM network as far as I know. All right, I'm actually based in Thailand, so I don't know a lot about the American networks. like.
AT&T does actually have GSM.
They do. Okay. All right. There you go. Okay. So they suck, basically. That's the take-home message. All right. We can go back to the other attacks, which are slightly more interesting. There's the IMSI detach I really want to show you guys, but unfortunately cannot. So the next one, which I'm hoping I can demo for the guy who's doing the IMSI catcher, is IMSI flood. So basically what happens with the IMSI flood is you use the mobile phone to send a very, very large number of location updating requests with a random IMSI value, or basically an IMSI value that's not actually backed up by a real SIM card. And this is all pre-authentication, because what's happening is we're basically just sending our username. It's requesting a password from us, but we've gone already and we've sent another username, right? So the idea is that we want to try and overload the HLR or the VLR infrastructure and take down the network from inside. So if we can knock over their databases internally, then we can prevent other people from associating on the network, making phone calls, or making other usages of the network. Right? So the idea is that if we can take down the back end, nothing else works. Once again, like the reason I actually developed this attack initially was the idea was that people who are going on marches where they were going to be monitored by IMSI catchers would be able to carry basically a small phone like this that would be automatically flooding out a large number of IMSI requests, and that would either fill up or confuse the value of the logs within the IMSI catchers, basically to make that useless. So it was all like pro-anarchy, yay, black shirt stuff. But then I figured out I could actually take down a network instead, and that was even cooler. And I wouldn't piss off the police immediately. So all for that. Okay, IMSI flood. Once again, we use our evil attack phone. It sends an RA, like this does the full RACH, AGCH, LCH handshake. So this actually does open a channel. But then the message that it sends up, the location update request, has bogus IMSI information in it, right? So it goes to the BTS, the BSC, back to the MSC, and then it hits either the VLR or the HLR. So we can target that based on the MCC and the MNC, right? So if we're targeting the T-Mobile network, we'd set the first 5 digits of our IMSI to 56026. If we were targeting AT&T, it would be 560 dot whatever it is that they use. Probably FF for fucking fail. You need to open a new channel every single time. So the question was, can you reuse an existing channel? And unfortunately, you cannot. Once you do the location update request, it will send back a ciphering request. So it'll say, if you really are who you say you are, you should be able to, do this horrendously clever mathematical thing and use your known secret key. And we don't know that secret key. So we cannot actually continue on from there. So the network state machine will try and get us to authenticate. We cannot authenticate, but we actually don't care. We're just trying to get them to waste time. I mean, theoretically, we could just send garbage ciphering information back, and it would have to do the computation itself, which is expensive, before it can figure out that we failed. All right. So the idea, once again, is if we take out the VLR and the HLR, then no other SIM cards can actually use that network. So even though the rest of the network appears to be fine, the SIM card, basically you still have signal, you still are able to turn your phone off and on, do all that other stuff. The problem is you're unable to open a channel, because when you do a location update request and it tries to go back to the back end is down. So even though you can open a channel, you can never authenticate on it, and you can never do anything beyond that. I haven't tried this one in the wild yet. I'm a bit scared to, because I don't want to get arrested, but I did implement it. It's kind of cool. And if the guy doing the IMSI catcher stuff is not using GSM 1900, I should be able to flood his talk. So come to his talk for my demo. Okay, so we'll skip that. The cool thing is, right, this is, right, so anyway, that's IMSI flood. Awesome stuff. Cracking, you can knock over a network using only a small number of phones and a laptop. pretty awesome. Haven't actually tried it. It should work. If we have a legitimate IMSI, can we do something much cooler? And the answer is yes. Yes, we can do something much cooler. Okay, so getting someone's IMSI is actually very, very easy. There's a lot of online spammers, online systems that you can use for sending bulk SMS. And if you want to verify that the phone number that you have is a real phone number, they'll do HLR lookups for you. So you give them a batch of phone numbers and they will verify that these are real phone numbers, that they're turned on, and let you know back. They'll also give you additional information. For example, if you want the MCC and the MMC, that's just part of the IMSI, they'll give you the IMSI itself and other information like this. This costs 1/6 of 1 euro cent per phone number. So if you have someone's phone number, you can get their IMSI. And if you have their IMSI, you can keep them off the network. Okay? So what we can do is we can do what's called the IMSI detach attack. So what happened was the idea was that when you turn your phone off, your phone notifies the network that it is no longer turned on and it cannot be reached. Right? Everyone's tried to call their wife while she's out shagging someone else and gotten the phone is like no longer available and off the hook. Right? Sorry. Or a similar situation like that, right? So everyone's familiar with trying to phone someone and their phone is not available, right? What causes that not available to trigger is actually that there's been an IMSI detach. So when the phone turns off, it sends a message to the network saying, I'm being switched off now, mark me as not available, right? The beauty of this is it's unauthenticated, right? You only send the one frame saying, I'm now turned off, and it turns off immediately. Right? There's no, well, if you are who you say you are, you should be able to like turn on ciphering mode. Right? So this is written into the spec. And what this attack does is it disables that particular SIM card from receiving SMS or phone calls. Right? It was discovered by a Belgian guy, Sylvain Moonart, and yeah, he's very smart. He's been helping me with like implementing some of the stuff. But here we go, right? So what do? We take our evil attack phone, we attach to the BTS, so we have to get a full channel for this one. It goes all the way through to the back end, and it informs the HLR, right? Tells the HLR that the phone has now been switched off. When that happens, the SIM card is now no longer on the network. So any phone calls or SMS that comes in is going to go to the HLR and say, where do I route this incoming information? The HLR goes, you can't, he's not on the network, declined, right? Now, the beautiful thing about this is that the guy with the phone can still make phone calls and send SMS and see full signal, right? Because we're not interfering with any of that particular information. We're only telling the back end that he's been turned off. What Sylvain found out, actually, when he tested this himself, was that when you do the detach attack, when you inform the HLR that the phone has been switched off, it terminates any existing phone calls, right? So if you have this on a 30-second loop, just sending detach requests all the time, the guy will never be able to make a phone call that lasts more than 30 seconds, right? Like it'll immediately cut him off. So.
Does that packet have to come from the same BTS?
No, it does not. It can, like, basically, because there's no security software in here at all to check for that information, right? Like, if they were intelligent, what they would do is they'd say, your last location update request came from Detroit. Now you're in, you know, Atlanta saying that you've been turned off. I think you're full of shit, right? They don't do that, no.
If you make a text message or a phone call after the session's been turned off, does it automatically update the database?
Yes. So the question is, like, when someone starts to make an SMS or a phone call, do they get automatically re-authenticated? And the way that the GSM network is implemented is yes, they do. Every time that they open a channel, they have to authenticate against the network, and that authentication is used to update the back-end information in the HLR. So if we combine this with like taking down all of the network or any other thing, like we could interfere with that. But as it stands right now, you can target one individual. So if you have their phone number, you can kick them off the network. So this demo is going to be fucking awesome. I was just going to take someone's phone number and then kick them off. But once again, yeah, it doesn't work. So if everyone could just imagine for a minute that their phone didn't work properly, and you couldn't get phone calls, and it wasn't because you were on AT&T, it was deliberate action, right? Then yeah, we could do that. Right, so those cover the GSM client-based attacks that I've implemented so far. So there's only 3 of them, but I've only been doing this for about a month or so on the client side. Prior to this, what we were working on is doing fuzzing against mobile phones because we wanted to be able to own everyone that walks by our office. And so for that stuff, we were doing baseband fuzzing. So we were using a malicious BTS to send packets and try and fuzz the baseband of mobile phones. So everyone's familiar with how a smartphone is actually made up, right? It's literally 2 separate CPUs. Usually they share RAM, but basically you have a phone like this, a feature phone, that acts pretty much as a modem. All it does is connect to the network, handle the networking stack, and then it will have a channel that's open to an actual operating system. So, like, for example, one of these things or one of these, right? These have a separate chip running the operating system. From our fuzzing point of view, we weren't actually interested in the operating system. We wanted to go for the baseband because the baseband has basically no user interaction, right? There's no like, do you want to authenticate this? None of that happens. The baseband is all pretty much done without any interference from the user, right? They can't have any access to it. So yeah, like we don't care about that part. We only want the other part. Yeah, cool. The other awesome thing about going after the baseband is most of them are written in C, and they were written in like the 90s, right? Everyone remembers how awesome the code was in the 90s when everyone knew about like integer wraps and how you had to be very careful about like sideness issues and so on. Yeah, so like fuzzing these things is quite cool. There's some downsides. Actually, there's a lot of downsides. The biggest downside for us is that we have no visibility on the phone. I'll get to that in a minute, actually. I've got a whole slide on why it sucks to do this. So basically, all the baseband does is control the radio and run several stacks and like try and appear to be awesome to the user, whatever. They use a real-time operating system. For the old versions of iOS, up until 1 through 3, they used Nucleus OS. Now they use something called ReactX or React Thread. Jeru was telling me about it last night, but I was very drunk, so I don't remember. Anyway, okay, so basebands are the target that we're going after. The way that we've done this is we took OpenBTS, which is an open source project that uses the USRP, which is the Universal Software Radio Project, and we've modified it to allow third-party programs on the network to open a channel to a phone and send data. So we implemented over XML RPC is LCH open, LCH send, LCH receive, and LCH close. So we use the BugMine framework, which is a framework developed by a friend of mine, Beng Nagy, my coworker, and we use his case generation tools and his mutation tools to generate the GSM attacks that we then send over XML RPC, over OpenBTS through the USRP to the phone, right? And it's all done over Wi-Fi because I don't like wiring up my house. So it's fairly cool stuff. It's also very targeted because we use the IMSI to open a channel to a specific phone. There's some problems with the way it works because if we everyone remembers from the RACH and the AGCH, it's all asynchronous. So we can inform a phone that it needs to open a channel, but we have no way of knowing that that channel has been opened until the phone authenticates to us, right? So we can see that a channel has been opened, but we don't know by which phone. So when we're fuzzing multiple phones, if we knock one of them over, we then get the channel request that we believed was for phone A will be for phone B when it shows up again. So that's a little bit annoying. Far more irritating is the fact that we have no visibility, we have no instrumentation, right? So all that happens is we make a phone reboot, and we detect this by using ping. You might have heard of it. It's a very sophisticated tool. It can monitor whether a phone is on a Wi-Fi network or not, and if it's not on the Wi-Fi network, we detect that the phone has crashed, and if it's crashed, we assume that it was some data we sent previously. And so it's very, very hard for us to go from fuzzing attacks, which we know make a phone reboot, to usable exploits that we can use to own people when they walk by. which kind of sucks because like it would be really, really awesome to have a backpack that you could walk around and it would just own people simply by having them be within radio range. Right now in our fuzz farm, we've got, well, we don't have the iPhone and the BlackBerry because they're with me, but we have the Nexus 1, Palm Pre, Nokia N900, and we also have some MTK phones, but we're not particularly interested in those right now. Here's a picture of what it looks like. It's very sophisticated. It's very dark, actually. I don't think you can see it. There's a laptop and a USRP and a phone. Pretty awesome stuff. No, typically what happens is basebands are purchased separately by, like, so HTC will go out and say, like, all right, we need a radio and it needs to do 3G and UMTS, and they'll find a commercial vendor who will sell them a baseband plus a radio, and then they just plug it in, right? Apple writes their own, BlackBerry writes their own, and Nokia writes their own. The Nokia one is called BB5. I'm not sure what the BlackBerry one is called. I've got some friends who have rim jobs around here, and they can answer. But like basically, people that care a lot write their own. Everyone else just buys a commercial version. They're not particularly sophisticated. Usually, like the Nokia interface is something called PhoneNet. It's now integrated into the Linux kernel. So there's a separate protocol based on sockets for talking to the baseband on a Nokia device. On the iPhone, the interface is basically the old Hayes modem, like ATD, 1, 2, 3, 4. Like that's how your iPhone talks to the radio. It treats it like a modem, right? Most phones actually act like that. It's the easiest way. It's a common interface. Here's a picture of some phones that have attached to our fuzzing. It's called the Cosic GSM Fuzz Farm. What would happen is when a phone associated with the BTS, they would get an SMS saying, "Welcome to Cosic Fuzz Farm." I was running this in my condo, and what happened was one day I came home, and when I got out of the elevator, I got an SMS saying, "Welcome to Cosic Fuzz Farm." So I had to run back, just pull out all the antennas, and I changed it. So the new message actually doesn't say this anymore. It says, like, get your best erotic ads at blah, blah, blah. That way they'll never know it's me, right? So yeah, that basically covers it. We've gone over like the fuzzing setup that we have, the fact that none of the bugs we find from that are any use to us, the different attacks that we can do from a phone to the network, some of which are quite cool, but none of which work over here. The primary takeaways from this is for a very long time, GSM security has been based on the idea that GSM is a walled garden. The only people who had access to it were people who could do very, very complex programming and had access to expensive equipment. Now there's a lot of open source stuff available, and you need a €5 phone. You can make your own cable for next to nothing, and you can start hacking GSM. So there's going to be a lot more issues with GSM going forward. There's a lot more people getting interested in it. The USRP stuff means that OpenBTS is allowing people to set up fake base stations, and they can do interception attacks, IMSI catchers, other stuff like that. So yeah, like GSM's basically fucked, which is why I'm now starting to look at how I can do attacks against 3G. So in the future, most of what we look to do is we want to do more fuzzing against GSM stacks, hopefully get some visibility by someone who's really good at hardware, getting JTAG onto one of these boards. And we want to look at 3G and start going after 3G soon. So a big thanks to the Osmo BB guys and the OpenBTS guys, because I use their software extensively. And you've got 4 minutes for questions. Better ask them now, because I'm going to be drunk later. All right.